Okay, so if you remember on Monday we were discussing that one of the fundamental objects that we could study was this operator, this matrix elements. X prime, and we define this as some G, X prime, X, and T. And we had shown that if we know this object, we can determine the energy eigenvalues, the eigenfunctions, the time evolution of any initial state, etc. So everything was kind of encoded in this one. We could do statistical physics of our quantum mechanical systems. Now, do you have any questions before we continue? Today, what we will be doing is just try to evaluate this explicitly. Now, to avoid some non-convergent integrals, rather than this object, let's first study this one. Or let's keep it that way. Now we said that this is nothing but we have a state. This is a particle localized at x. It corresponds to a Dirac delta wave function. This whole thing is nothing but exactly the same state evolved for a time t. And so we are kind of looking at, we start from with a particle localized at the point x. This is the amplitude for this particle to be at the point x prime at a later time t. And rather than looking at this time evolution by t sec t duration of t as a whole, we can just divide it into small parts. We can just say that, okay, let's start with x. Then we evolve it by epsilon. Another epsilon. Epsilon. And then eventually we have the x prime. Let's say we have n of these, and n times epsilon is just our t. So we didn't really do anything. H commutes with itself, so the exponent of two functions of h is just the exponent of the sum of those functions. Now, once we do this, we can use the identity. You see the identity, we can write the identity in this form. This is 1, x ranging from -infinity to infinity. So we can just insert this identity here, 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 etc. in n-1 places. So we would then obtain, this is equal to the integral, let's say of dxi. We have n-1 of them. And then we have x prime e to power -I over h bar h epsilon x n-1. Now this is the product. Then x n-1 e to power -I over h bar h epsilon x n-2, etc. x1 e to power -I over h bar h epsilon x. Now, just for notational simplicity, let's call x to be our x0 and x prime to be our xn. So we can write exactly the same thing as the product from I is equal to 1 to n-1 of dxi xi e to power -I over h bar h epsilon xi-1. Now this time all of this is in the product. We are still missing one x e to power -I over h bar h epsilon xn-1. Just a different notation. And all the xi goes from -infinity to infinity. Now, eventually we will take the limit as epsilon goes to 0. Now, what we are actually doing here is, we already said that each one of these matrix elements is nothing but the amplitude for the particle to go from x to x prime in a time t. Now, if you look at each one of these terms over here, this is the amplitude that if you start from a particle located at xi-1 in a time epsilon, this is the amplitude for that particle to go to the point xi. So this is our particle. we start, this is as a function of time, this is x. At t equal to 0, let's say we are at x0, and then at t is equal to t, which is n times epsilon, we are at some other point x prime. Now what we did was we divided this time evolution into intervals of length epsilon. These are each, they have length epsilon. And then we wrote the amplitude that this particle starts from x and goes to x prime into the several products. So we first, let's say, this is x1, this is x2, this is x3, x4, xn minus 1. So the whole amplitude for the particle to go from x to x prime is the amplitude that it goes from x to x1, then the amplitude that it goes from x1 to x2, then from x2 to x3, x3 to x4, etc., from xn minus 1 to x prime. And of course, we are also integrating over x1, x2, x3. We are, in a sense, you can just think of those integrations as summing over all possible different values of x1, x2, x3, x4, etc. But if you change x1, x2, x3, x4, you are basically creating different paths that go from x to x prime. And if you are summing over all possible values of x1, x2, etc., you are nothing but summing over all possible paths that go from x to x prime. Now, of course, if the epsilon is finite, it can be such a broken path. But in the limit as epsilon goes to 0, it just goes to a continuous path. Only the continuous path will contribute in the limit as epsilon goes to 0. Now let's continue the evaluation of this term. We have such terms, xi minus 1, and we will assume that h can be split into two parts. The kinetic term, which depends only on the momentum operator, and the potential term, which depends only on the coordinate operator. Well, almost all the Hamiltonians that we studied could be written in this form. Then, of course, we have in this exponent terms that depend on momentum and the coordinate. Now, since t and v, they do not commute, in general, this is not equal to e to the power minus I over h bar epsilon t plus v. In general, they are not equal to each other. No, t times, sorry. They are equal, but they are not equal to this one. But what we can do is, if you just compare the left-hand side and the right-hand side, this is 1 minus I over h bar epsilon t plus v plus of the order of terms of the containing epsilon squared. If you just expand the right-hand side, this is 1 minus I over h bar epsilon t, 1, this is minus I over h bar epsilon v, plus terms of the order of epsilon squared. But the right-hand side, I can just expand each one of these parentheses, and it will be equal to 1 minus I over h bar epsilon t plus v plus terms of the order of epsilon squared. So as long as I can ignore terms that are proportional to epsilon squared, the left-hand side and the right-hand side are equal. This is equal to e to the power minus I over h bar epsilon t, e to the power minus I over h bar epsilon v, plus terms of the order of epsilon squared. And eventually, in the limit as epsilon goes to 0, those corrections will just disappear. So what we can do is, Okay, this is what we were trying to evaluate, epsilon xi minus 1. This is equal to xi e to the power minus I over h bar epsilon t e to the power minus I over h bar epsilon v xi minus 1, of course, plus terms of the order of epsilon squared. I can insert an identity over here again. Now, since both of these, one of them depends only on the momentum, the other one depends only on the coordinate, I can insert an identity, let's say, of momentum. The coordinate, that v, I can already take it out, because v acting on xi minus 1 just gives me the value of the potential at the point xi minus 1. So we can just insert the identity, and then we have xi e to the power minus I over h bar h epsilon xi minus 1. This is equal to sum over all the momenta, xi e to the power minus I over h bar epsilon t p e to the power minus I over h bar epsilon v xi minus 1. Well, let's say this is pi. And this will become the pi e to the power minus I over h bar epsilon momentum, the kinetic energy corresponding to the momentum pi, times e to the power minus I over h bar epsilon times the potential at the point xi minus 1 times e to the power I over h bar pi xi times e to the power minus I over h bar pi xi minus 1 divided by 2 pi h bar. Since we are in one dimension, it's just 2 pi h bar. In 3 dimensions, I would have cube. This comes from the normalization of the plane waves, the matrix elements between xi and pi. So basically, this is what we end up having for each one of these. This is equal to integral of over pi. Now, in this last expression, none of them are operators. I don't have any operators left. Everything is just functions of numbers. Because the operators already acted on states, and we picked up the eigenvalues in those states, which are just numbers. So I don't need to worry about the commutation relations anymore. So this is e to the power I over h bar pi times xi minus 1 minus times epsilon, no, not epsilon, minus epsilon times h pi xi minus 1. Now let me define a function. Well, let's say 2 functions at this step. X of t, this is equal to xi, where t is equal to epsilon times I. And p of t is equal to pi when t is equal to, again, p is equal to epsilon times I. So these xi are just a collection of numbers, nothing more. But then I define a function which goes over all these numbers. Basically, it can be any functions that just crosses these points. So if this is the case, let's say we have xi minus 1. This is equal to x of t minus x of t minus epsilon. But this is x of t minus x of t minus epsilon over epsilon times epsilon. Remember, eventually I will take the limit as epsilon goes to 0. If I take that limit, this is nothing but dx by dt times epsilon. So this matrix element this is dpi times e to the power I over h bar times epsilon times p x dot minus h. At the time, let's call it ti. So does this combination remind you of anything? You have already taken classical mechanics. Most of you took classical mechanics, right? PQ dot minus H. This will be the Lagrangian. Not yet though, it's, for the time being it's PQ dot minus H. Not really the Lagrangian yet. That is where we are kind of heading to. But let's just keep it there for the time being. So now we can just go back to our expression. This one. I can just put all those matrix elements over there. So I would have sum over, integral over all the dxi's, integral also over of all the momenta times e to the power I over h bar epsilon px dot minus h times ti, sum over all I. But again, I will eventually take the limit as I goes to 0, epsilon goes to 0, n goes to infinity. Well, in that limit, that is nothing but an integral. From 0 to, let's say, final time t. Now, what we had done over here, this is also quite most of the time written in this form. These weird symbols. This is equal to product of dxi in the limit as n goes to infinity, epsilon goes to 0. And similarly for the momenta. Yes, so here we can pick up the mathematician among us.
Are these valid in mathematics?
Mathematically, well, there are some shortcomings, let's say, but we can. You see, before taking these limits, everything is well defined. We just have a huge number of integrals, and which you can deal with them on the computers. Now, let's do one more step. Now, we will make one more assumption and say that t is equal to p squared over 2m. Because with this assumption, well, I will go back to this expression over there. With this assumption, I can integrate over the pi, over all the momentum. Let me take this expression. Well, the definition, by the way, of this expression over here is actually this one. This is how we define it. Of course, there is a problem of convergence. Does it converge? Is it well defined, etc.? But it works. And for the physicists, for us, that's most of the time enough. It works. So we leave it to you mathematicians to prove that it makes sense. So this becomes dpi e power I over h bar. Let me write pi xi minus 1 minus epsilon pi squared over 2m times e power minus I over h bar v of xi minus 1 times epsilon. I don't need to worry anymore about the commutations. Again, I repeat, these are just numbers, ordinary functions. That's kind of the nice thing about these path integrals. So you don't need to worry about the operators. So this becomes dpi e to power minus I epsilon over 2m h bar pi squared minus 2m over epsilon xi minus 1 times pi. This we can just complete it to squares, and then it just becomes the Gaussian integral. So that becomes square root of 2m pi h bar over I epsilon. That is the result of the Gaussian integral. We still have what is left is minus I epsilon over 2m h bar m over epsilon xi minus 1 squared, and yeah. Oh, this is nice. So I just added this term. No, sorry. Minus 1 times this one. I just added this term to the above, within the above square brackets, and then subtracted it. That's why I have that additional minus 1. And let's just simplify this a bit. 2m pi h bar over I epsilon e to power I epsilon over 2m h bar m squared times x dot, let's say, at ti. X dot at ti is just xi minus 1 over epsilon. This thing is squared. And these m's also cancel. 2m pi h bar over I epsilon e to power I epsilon times 1 over 2m x dot squared. 1 over 2 mv squared, basically. Now, if we use this result for this matrix element, xi minus 1, and put it in our above expression, if you remember, we have the integrals over all the xi's, and then these matrix elements. We have n of them. So g x prime x t just becomes sum over the xi e to power plus I epsilon. I have an h bar over here. I epsilon over h bar, sum over 1 over 2m x dot squared minus v of x. Now v of x, I forgot to write over here. I have this e to power minus I over h bar epsilon v So that's why I still have this one. Now it is the Lagrangian. 1 over 2 mv squared minus the potential. And again, if we just take the limit as epsilon goes to, I also have these factors, 2 m pi h bar over I epsilon to the power n, right? Yes. Hmm? All these factors over here. Hmm? N over 2. Right. Two m pi h bar over I t times n to the power n over 2. If we didn't forget any other factor of n's, etc. And then we have this measure over x e to power I over h bar dts. Now, of course, the limit as epsilon goes to 0 is kind of problematic. That is the limit as n goes to infinity. Now, the thing I don't like is about this t to the power n over 2. This is what we seem to obtain. Let's do some practical applications. One example that if you remember, we had discussed on Monday was the free particle. We can calculate the path integral of the free particle and just see if it matches with our previous result. And if it doesn't, then we can look for where we made the mistake. Now, for the free particle, v is just 0. So g x prime t is 2 m pi h bar over I epsilon to the power n. Then we have these integrals over all values of xi, I from 1 to n minus 1. We have n minus 1 of them. And then in the exponent, we have e to power minus I over plus I over h bar, sum over 1 over 2 m xi minus 1 squared over epsilon. Now let's start taking these integrals one by one. Let's start with x1. Now you see, before going that way explicitly, look at this expression. Let's see this one. For the time being, let's forget about the overall exponent over there. Now that will be, let's just leave it epsilon, not T over N. Now that factor over there is just a normalization. It's just a constant. Epsilon is constant, N is constant for a given choice. That's just a normalization of this G. And normalization shouldn't really make any effect whatsoever. What is important will be, we are summing over all possible paths. And in quantum mechanics, if something can happen in more than one different way, what you do is you just calculate the amplitude for each one of those ways, and then sum the amplitudes, and eventually take the square of that sum. So that is basically what we are doing over here. We are assigning an amplitude for each path for the particle. The particle can take any path for going from point x to x prime. For each one of those paths, we assign an amplitude. By the way, if you look at this amplitude, the amplitude has the same absolute value for each path. Every path has the same, they don't have the same amplitude, but nevertheless, the amplitude they have has unit norm, a constant norm. And then eventually what we do is we just sum all the amplitudes and then whatever you want to do with that. So it gives us the total amplitude to go from the point x to x prime. So this is basically what we had obtained. We obtained that the amplitude for each path that you can imagine is just determined by the way, the classical action corresponding to that path. Now, this also tells us why we have the classical limit. You see, classical limit is the limit as h bar goes to 0. Now, if you look at all those paths, they are oscillating. They will be oscillating wildly. So if h bar is, if we formally assume that h bar approaches 0, they will oscillate wildly. I mean, if you have one path, then even the neighboring path will be so different from the original path that they will probably differ in sign. So when you sum them up, you will get 0. Of course, unless when you change your path slightly, S might not change at all. If when you change your path slightly, S doesn't change at all, then there won't be any cancellation. But for all other paths, there will be a huge cancellation. And this condition, we can write that in the limit h bar goes to 0, only the path, this is L. This whole integral is our action. Only the path that satisfies delta S is equal to 0 contributes. Because all the other paths, I mean, there will be one path, then you change it slightly, you are also supposed to sum the contribution of that path, but they will differ in sign, so they will cancel. So basically, schematically, you can say that let's say this is x, this is x prime. You will be summing the contribution of this path, this one. You will be summing them all. And then you have the classical path, let's say it is this one. So if you just consider very small variation around this classical path, they will add constructively. But if you consider the other paths that are very different from the classical path, and if you consider slight variation around that path, they will interfere destructively. So they will not contribute. So basically you have the emergence of the classical physics. So this is the only path that will have a significant contribution to this amplitude. So this is basically the part that the mathematicians do not like. It goes to infinity in that limit. But that's just a normalization. Now let's evaluate this one. Now we will also do it later on also for the harmonic oscillator. Let's integrate x1. Now we will not be integrating n-1 integrals, but what we will be trying to do is just try to figure out some pattern. And once we obtain a pattern, then we can just generalize it to n. Integral over dx1 from minus infinity to infinity. Let us write the terms that only contain x1. How many terms do I have that contain x1? Not 1, 2. You see, we have 1 over 2m x1 minus x0 over epsilon squared, and also x2 minus x1 over epsilon squared. I have 2 terms. This is equal to minus infinity to infinity dx1 e to power I over h bar m over 2. Well, there's also epsilon over here, so let's take the epsilon squared out. What is left is twice x1 squared minus twice x1 x2 plus x0 and plus x0 squared plus x2 squared. Now the x1 squared integral, I can just convert it into a Gauss integral. Let me also cancel these 2's. So the Gauss integral will be square root of pi epsilon h bar over minus im. Well, this is, I'm just taking pi over the coefficient of minus x1 squared. E to the power I over h bar m over epsilon. Well, first of all, I already have terms that do not contain on x1. And then I have the, when I complete it to squares, I will get an additional term, so I have to subtract that one, and that will be x2 plus x0 squared over 4. Well, this epsilon over here is nice. Well, it is nice because, remember, we have all these factors of 1 over epsilon in the coefficient. So that epsilon will cancel that 1 over epsilon. From each one of those integrals, we will get some 1 over some epsilons. Let us just try to simplify that factor. Pi epsilon h bar over minus I m. Well, that minus I is also nice because when I multiply it with I, it will just give me 1. A to the power I m over 2 h bar epsilon. Let's say 4 h bar epsilon. I have x2 squared plus x0 squared. No, this is twice x2 squared plus twice x0 squared minus x2 squared plus x0 squared plus twice x0 x2. Now these will cancel, one factors of x0 squared and x2 squared. So we are left with m epsilon h bar over minus I m e to power I m over 4 h bar epsilon x2 minus x0 squared, or square root of m epsilon h bar over minus I, no, this is pi, m e to power I m over 2 h bar epsilon over 2 times x2 minus x0 over epsilon, all of this thing squared. So kind of we seem to be on the right track. Now this just looks like each one of these terms over here. You see we had m over 2 epsilon over h bar xi minus 1 over epsilon squared. Now we integrated over x1 the terms, integration over x1 basically combined x0 and x2 in such a way that it just looks as if xi didn't exist. The modifications is that we have this overall factor over here. That is one modification. And also instead of epsilon, we now have epsilon over 2. Okay, is that factor 2 correct? I think I will keep it here. Let's see if this pattern is general. Let's repeat it for x2. Now we have this x2 integral from minus infinity to infinity. We have e to the power, let's go back. Now from this integral, x2 appears again in two terms. There is the x3 minus x2 squared term, which we didn't take into account in our x1 integration. So we have to keep it as it is. We call I over h bar epsilon m over 2 x3 minus x2 over epsilon squared. This is a term which contains x2. There is also x2 minus x1 squared term, but that term after integrating over x1 just turned out to be this term. So let's also add that one. I m over 2 h bar epsilon over 2 x2 minus x0 over epsilon squared. This is equal to minus infinity to infinity dx2 e to the power I epsilon m over 4h bar, and then we have twice x3 minus x2 squared plus x2 minus x0 squared let's open up the exponent. Twice x3 squared minus twice x3 x2 plus x2 squared plus x2 squared plus x0 squared minus twice x2 x0. This is equal to minus infinity to infinity integral over x2 e to the power I epsilon m over 4h bar. Let's see, terms that do not contain x2 is twice x3 squared plus x0 squared. Then I have the plus twice three times x2 squared. And then I have x2 over here, minus twice x2, twice x3, plus x0. This is equal to from minus infinity to infinity dx2. Well, we can directly take away the x2 integral. Or let me just write one more line. I will take that 3 out, 3 over 4h bar. So x2 squared minus x2 minus twice x2 twice x3 plus x0 over 3 plus twice x3 squared plus x0 squared over 3. Now I can take the x2 integral. The Gaussian integral just gives me pi times 4 h bar over minus I 3 epsilon m under the square root. I have terms that do not depend on x2, e to power I 3 epsilon m over 4 h bar times twice x3 squared plus x0 squared over 3. And well, I just add and subtract twice x3 plus x0 over 3 squared. Now let's simplify it a bit. 4 pi h bar over minus I 3 epsilon m e to power I 3 epsilon m over 4 h bar. Let's take the 9 also out. What is left is 3 times 2x3 squared plus x0 squared minus 4x3 squared plus x0 squared plus 4x0 x3. Well, let's rewrite it once more. E to power 3I epsilon m over 4 h bar times 9. 6x3 squared minus 4x3 squared is just twice x3 squared. 3x0 squared minus x0 squared is twice x0 squared. And then I have minus 4x0 x3. Four pi h bar over minus I 3 epsilon m e to power, well, this cancels 3I epsilon m over, well, let's cancel a factor of 2 also, over 6 h bar times x3 minus x0 squared. So let's combine what we have. We had the x1 integral. The x1 integral, our result was this one. This is the x1 integral. Then we take the x2 integral along with the x1 integral. Now our result is, by the way, where did I make a mistake? This pi. No, this epsilon. Now the mistake was over here. Here I have a 1 over epsilon squared. So epsilon is not in the numerator, it's in the denominator. So when we take the Gaussian integral, epsilon goes to the numerator. So now our result is pi epsilon h bar over minus I times m times 4/3. And the exponent is e to the power I m over 2 h bar times epsilon over 3 x3 minus x0 over epsilon squared. This is after the x2 integral. Now the pattern in the exponent is kind of obvious, well, already for me at least. You see, we evaluate the x1 integral. So now if you use this 1 over epsilon squared, we have 2 epsilon. Now we take the x2 integral, then we will have 3 epsilon. If we take the x3 integral, we will have 4 epsilon in the numerator. If we take the xn minus 1 integral, then we would have n times epsilon, which is t. So when we take all the n minus 1 integrals, we won't have any epsilons left in the exponent. It will be expressed in terms of the t. Now the coefficient in front is not so obvious for me for the time being. Oh, sorry, I forgot one more thing. This is the square. Because the second line is x1 integral and x2 integral. In the x1 integral, I already have that factor, which I didn't include in my previous calculation. So I have to add it. So that power is also kind of, it will be nice. It will be n. I will have epsilon to the n. And remember, in our definition of my path integral over here, I have 1 over epsilon to the n. Well, to be more precise, it should be 1 minus 1. There also I will have n minus 1. I have n minus 1 integrals. Each one will bring a factor of epsilon. In the definition of G, I have 1 over I to the n minus 1. Here I have 1 over minus I to the n minus 1. They will just cancel each other, etc. So epsilons will just cancel. In fact, that factor will just cancel most of it. But this 4/3, well, basically, I don't know what the pattern is. So what we need to do is the h3 integral. But that I will just do after the break.